All right, then thank you. Yeah, so I'm Markus. I'm working at the Department of Material Science and Metallurgy here in Cambridge in the lab of Professor Judith Driscoll, who is a fellow of Trinity College. Thank you for having me, and thank you everyone for attending this presentation. So in the next 20 minutes or so, I will try to convey to you why our research into new forms of computer memory is important. To begin with, we can look at this figure here, which I took from a study from 2015, where the authors tried to project how much of global electricity consumption would be due to information and communication technologies. So ICT in short, that means our usage of the internet, of computers, telephones, and so on. And we're here 2021, and even without looking at the exact numbers, it's quite clear that we can expect that the electricity consumption due to ICT will increase rapidly over the coming years. And in an expected scenario, the authors think that by 2030, it will amount to at least up to 30% of worldwide electricity consumption. In a worst case scenario, it could even go up to about 50% of this. So it's quite clear that, especially in the light of our ongoing climate crisis, we once again need to flatten this curve and find more energy efficient hardware. And our research aims at this turquoise portion here, mostly the use of data centers, anything that has to do with the storage of information. So we're looking into more efficient memory. To narrow this down a bit, where the data storage comes into this, we can look a bit closer at such data centers. So data centers are massive buildings all around the world, crammed full of computers. You can see an employee walking through racks of computers here in an example from inside a data center. Here we have an example from the Google data centers all around the world. And then you can add dots for like Facebook, Amazon, Twitter, you name it. And we'll see that pretty soon there will be dots everywhere, computers everywhere, which use a lot of energy. So there's an immense potential to save in this energy. And to narrow this down further to see where the physical memory actually is, we can look into one of these computers. I will illustrate this by just a normal personal computer that many of you might have at home. In a similar way, this will be for laptops and phones. So if we open a computer, we'll encounter a circuit board like this, where different components of the computer are mounted. We have the processor, which is the central unit of the computer, so to say, the brain of the computer, where the data is processed and where all the calculations are carried out. And attached to this, we have the first instance of memory, the so-called cache. It is the smallest, but also the fastest type of memory in a computer. And in terms of our mind, this would probably be closest to something like our subconsciousness. Then next, just like we have, a computer has something like a short-term memory. This is called random access memory. It's larger than the cache, a bit slower, but not by very much. And finally, the largest portion of memory in our computers and servers is the storage. So this is where all the data really is stored for long-term. All the photos on Facebook and Instagram, all the videos on YouTube, they are somewhere in such a storage inside some server in a data center. Now, when looking at the different time scales here, you can see that the long-term memory here operates on a much slower time scale than these fast memories that I mentioned before. And this is not very efficient, of course, because any data that has to be processed, so either read it from the storage to do some calculations with it or save it for later. When the processor and these fast memories want to interact with the storage, for a long time, they're just sitting idly, not doing anything, because they have to wait for the storage to tuck away the data somewhere. But while sitting idly, they still consume some small amount of power. So this is clearly not very efficient. The second and more important problem here is that this fast memory is volatile. That means the information stored inside it will be lost when the power is switched off to the memory. And even worse, the data is stored in the form of charge somewhere on these chips, and charge constantly leaks away. So the information is not only lost when the power is switched off, but it's leaking out all the time and has to be restored all the time. And this takes energy all the time. So this is a very large inefficiency for these fast kinds of memory. For the non-volatile storage, so just think of your USB stick, for example. If you plug it out of the computer, the information is still there. It is not lost. But on the contrary, for once, it's much slower, as I pointed out, and it also requires higher voltages to store the data to begin with, and thus it uses a lot of energy here as well. Now, it would be really neat if we could combine the positive things of all these different kinds of memory and make a new super memory, in a sense. So we would like this kind of memory to be fast, non-volatile, and consume only little power. Such a kind of memory is often referred to as storage class memory, so that's the acronym SCM, or more general emerging non-volatile memory. And this is what we're looking into in our research. Now, to build such a super memory, we need 3 basic ingredients that I will present in the following. And the first one is the structure of the materials that we use on an atomic level. So any solid material can take some different shapes, some different order to the atoms they're made up of. The simplest maybe looks something like this. So it's quite chaotic. We call this an amorphous material. So there's no order to the arrangement of atoms in the material at all. In stark contrast, a crystalline material is very well ordered, as we see here. So the first thing that might come to mind when thinking of crystals are like pretty gems and jewels. And indeed, they are examples for crystalline materials, but it's really a much more general concept. So a crystalline material just means that the arrangement of atoms inside the material is well ordered, and one specific so-called unit cell, so the smallest structure in it, in this case, this hexagon, is repeated regularly throughout the whole structure. And we'll need such a material to make our memory cell, as I show you in a slide or two. First of all, we can make such materials in the lab. Our lab looks like this, so appropriately chaotic, but every item here has its function. And what we need here now to make such nice crystals is mainly the orange box here in the background and the vacuum chamber here in front. So the orange box is a laser of high energy. And in order to see how we make these crystals, we can take a closer look through this window here. This is where the magic happens. This technique is called pulsed laser deposition. So what happens is that the laser shoots short pulses of high energy into this chamber onto what we call a target. So it's this white disk here. This is an amorphous material, and the high energy of the laser evaporates atoms from this material into a plasma plume. And because the chamber is evacuated, so it's under vacuum, the evaporated atoms can travel the length over to this heater here. So you see it glowing bright orange. And by controlling the ambience in this chamber, so the pressure, the energy of the laser, the distance, the temperature, and so on, we can make these evaporated atoms form very nice crystals here on the substrate on the heater. However, as hard as we may try, it's very difficult to make such perfect materials, and usually there are always some defects in the material, so dislocation, something like this. The materials that we're looking into are mostly oxides, so compounds of metals, transition metals, and oxygen. In this schematic here, I represented oxygen as the red dots, and one of the most common material defects in oxides are oxygen vacancies. So that means in this beautiful crystal lattice, there are some sites where there should be oxygen atoms, but they're missing. So these are oxygen vacancies. And while I called them material defects, we actually want to use these defects in making the energy efficient memory. And I'll show you how just in a second. So before making any devices out of this, however, we want to make sure that we actually have the crystal structure and the materials that we want to use. For this, we have some different techniques at our disposal. So just point them out briefly to give you an idea. So we can use atomic force microscopy to measure the roughness of our materials and the thickness. In this case, we measured a thickness of about 40 nanometers, so everything is very small. As Professor Grosche just mentioned before, we can use X-ray diffraction to determine the crystal structure of our materials. So in this technique, we shoot X-rays at the material, and if it's crystalline, the order of the material will form planes which can diffract the X-rays, and by measuring the angle of the diffracted X-rays, we can then calculate the crystal structure that we have. So this would be an example for this. So we measure the intensity at different angles, and the peaks are in characteristic locations for different materials. Then finally, we want to know if we actually deposited the elements that we want to deposit. For this, we can use X-ray photoelectron spectroscopy. So this measurement was carried out by my colleague, Megan Hill, just 2 weeks ago or something. And in this technique, we use X-rays as well. But this time, we want to use the energy of the X-rays to kick out electrons from the materials, because the binding energy of electrons to their atoms is characteristic of different elements. So if we measure the energy that we need to kick out electrons out of a material, we can then see what materials we have in our film. And with these two together, we know the crystal structure and we know the elements in the crystal structure. We can then be quite certain that we actually get the materials that we want. Now, the second ingredient that we use to make memory devices is the fact that these oxygen vacancies that I introduced before can move inside the materials. So the atoms in a material are bonded to each other with a certain energy. And if we supply enough energy to the material, we can break these bonds and the atoms can move around a short distance before they are bound to the next side. So if we can break the bonds of an oxygen atom, for example, to its neighbors, it can switch place with the oxygen vacancy. Then we're in this situation, and effectively the oxygen vacancy moved up through the material. Now, because of the distribution of atoms and electrons in the material, the oxygen vacancies carry a positive charge compared with their surrounding, and we want to make use of this as well. The final ingredient that we need is a basic understanding of the transport of electrons in our materials. And when we make a device such as sketched out up here, so we take the material that we just fabricated and sandwich it between two electrodes, these are the black contacts, then to an electron traveling from one electrode to the other, the electron will experience something like this. So there will be a barrier for the electron that blocks its path. And if the electrons have enough energy, they can jump over this barrier, or if the barrier is thin enough, they can also tunnel through it. This is a quantum mechanical effect. Either way, the amount of electrons getting from one electrode to the other, so from up here to down there, depends on the height and the thickness of the barrier. And the height of the barrier is now what we finally use to encode information. So what we can do with this technique that I showed before, pulse laser deposition, is to make such heterostructures here. So we can make pillars of one crystalline material inside a matrix of another crystalline material. And why we do that is that we can combine materials such that inside the pillars, these oxygen vacancies can move around relatively easily, but they cannot do so in the other material. So by this, we can define channels along which the oxygen vacancies can move back and forth. Here is another characterization technique for crystalline materials. This is transmission electron microscopy, and we can actually see that we really get these pillar structures. This is from a paper that Professor Driscoll published with her students a few years ago. So now we have all the ingredients. If we put them together, we can make a memory cell. And how this works is as follows. So we continue with this structure that I introduced here. We have our material sandwiched between two electrodes. And if we start here and say the oxygen vacancies are distributed randomly throughout the material, we have this situation here with a certain barrier for electrons. But if we now apply a positive voltage to one of the electrodes, M2, for example, now because the oxygen vacancies are charged positively as well, the positive voltage at the electrode will drive them away and closer to the other electrode. But like I said, they are kind of confined to these pillars, so they cannot get out. And this means that they will accumulate at the interface to this other electrode. Now, the accumulation of positive charge at the interface means that the barrier that the electrons experience will be lowered, as I indicated here. And then with the ingredient that I pointed out before, we can change the height of the barrier by moving around the oxygen vacancies in the material. So if the barrier is lower, more electrons can get over it to the other side. If we reverse the voltages and instead apply a negative voltage to M2, the second electrode, then the positive oxygen vacancies will be drawn back into the material and the barrier assumes its previous state. So we can switch back and forth between these two states. So this seems to work fairly well. I measured these current versus voltage curves in our lab the other week, and this reflects exactly what I tried to point out. So if we start with 0 voltage at one of the electrodes, increase the voltage, we get some current, and at the same time we accumulate positive charge at the other side of our little device. So that means when we go back, now we have this accumulation, the barrier is lower, and for the same voltage, we now get a higher current than before when going back down to 0. And in the other direction, again, first, the oxygen vacancies are still accumulated, so we get a fairly high current. But at the same time, we're pushing them away from the interface so that the barrier becomes higher again. And when going back to 0, now the current is lower than it was before. So we have 4 branches in this current versus voltage curve. And we can identify this with a certain resistance to the device. So resistance is just the voltage divided by the current. So if we take some arbitrary voltage here, either we divide it by the larger current or by the smaller current, and this means we get 2 different resistances. This is sketched out in the figure down here from the same paper as these images. So we see that the resistance switches between 2 distinct states, a very high resistance and a low resistance, and we can switch between these states back and forth thousands and thousands of times. Now, computer information, any information in the computer is stored in a binary alphabet, so either as a 1 or a 0. And we can now simply just identify one of the resistance state as 1 and the other as 0. So we can store information in the resistance of such a cell. And because all we have to do is push back and forth some atoms, this requires very little energy. It can happen very fast, and it is non-volatile, because as soon as we remove the voltage, the oxygen vacancies don't have the energy anymore to move back, and they will remain in their position. So this is very promising. It's exactly what we want to achieve. Before I conclude, just briefly, besides this approach of controlling the interface between different materials, there are also other approaches. So one other that we are exploring in our lab is called, or is based on ferricity, but others use other properties of the materials. And this is very good because while the results that we have look quite promising, there are still challenges remaining. And if we have different paths to such better memory in parallel, then it's much more likely that we will actually find a solution in the end. So with that, I conclude. I hope I could convince you that reducing the energy consumption in information and communication technologies is very much a materials challenge. Not only we need to cooperate with other fields, of course, but the underlying materials play a very important role. There are several different promising perspectives to achieve the memory that we want: low energy, high speed, non-volatile. And the challenges that remain are that we have to make or design these materials so that they are compatible with industry standards, with fabrication, with availability of materials and so on. So I would conclude by saying that the solution is still in the lab, but it's looking good that we can find a solution and reduce the energy consumption of ICT for the future. With that, I'd just like to thank our funding agencies, and once again, thank you very much for your attention.
Dr. Hellenbrand, thank you very much for the great talk. So now we have a very short time for questions. So if you have any, just ask them either in the YouTube chat or raise hand in the Zoom call. Okay, we will give them a minute or so. And you have, like Judith Driscoll wrote in the YouTube chat, brilliant talk, Markus. Thanks for representing the memory work from our group so clearly.
Well, thanks, Judith. Great that you could attend.
Okay, so there's a question. Thanks for such a nice talk. What are the advantages of interfacial RMAs over filamentary RRMAs?
Mm-hmm. So they're both present in this overview that I showed before. Just for the others who might not be familiar with this, in filamentary devices, we also use the movement of oxygen vacancies inside a material. But what happens here is that they form a continuous path from one electrode to the other. So then the electrons can travel along a chain of oxygen vacancies from one side to the other. The main challenge with this type of memory is that since the oxygen vacancies have to form a very well-ordered chain and thus move significantly more and with less control than in the interfacial devices, there is a reliability problem with these, because each time the filament is formed or ruptured again, it might look a little bit different than before, because the movement of the oxygen vacancies is pretty much random. So this is the difficulty with filamentary devices. The idea with interfacial devices is then that we define the channels along which oxygen vacancies can travel from the beginning. So they will not vary from switching cycle to switching cycle, but always follow the same path. And hopefully by this we can improve the reliability of this.